Well, welcome. Today is Thursday, February the 18th, here at Spain Park High School Advanced Level Chemistry. Yesterday, what did we talk about in our 25 minutes of class?
Composition.
Percent composition. Today, we're going to go in the opposite direction. Just give you an idea. Today, we're going to learn how to do empirical and molecular formulas from percent composition. We did percent composition given the formula. Now we're going to be given percent composition and have to determine the formula. Just kind of go in the opposite direction. There's going to be 6 easy steps to doing these problems, okay? And we're going to do that. We'll practice tomorrow in class. You're going to have a quiz on Monday, okay? It wasn't supposed to be on a Monday. It was supposed to be like on Thursday, but you know, oh well. So.
Wait, this is due tomorrow? Wait, is this
Yeah,
due
the
tomorrow?
percent, the gum lab's due tomorrow.
Okay.
All right, determining empirical and molecular formulas from percent composition data. That's what we're going to do. First off, empirical formula. We've already talked about this. What does empirical formula mean?
Simplest whole number ratio.
The simplest ratio, the reduced, like a fraction, is reduced all the way down. Ionic compounds use the empirical formula. So an empirical formula is the simplest ratio all ionic compounds use the simplest ratio. Now some covalent compounds do, like water, H2O, it's just the way the molecule actually exists is in the simplest ratio. But the molecular formula it's the formula of the actual molecule. And the key here is it does not have to be the simplest ratio. Okay, so empirical formula, simplest ratio, that's what we've kind of been dealing with. That's what your naming project is going to be all about, and kind of going from there. Now, if I look then and I say C6H12O6, that's glucose. This is the molecular formula. What's the empirical formula of this? CH2O. So we can see that this is 6 times bigger. It's a whole number, right? Does anybody know the formula for hydrogen peroxide?
H2O.
Okay, naming project, you guys got that one, okay? H2O2. That's the molecular formula. Peroxide actually looks like this, but what would the empirical formula be? HO. Right? So this is going to be times 2. So the molecular formula is twice as big as the empirical formula. Here, the molecular formula is 6 times as big. You guys put gas in your car. What's the 87, 91, 92? What do they call that?
Oh, I was just told always pick the lowest.
Premium, but I mean it's the blank rating. It's
My parents just told me to pick the lowest
I
one
hate
because it's the
getting
cheapest.
that's I told my car. I
Not
never give my
premium?
car the good stuff because I don't want it to get spoiled, and so I always give it the cheap stuff. But it's the octane rating. Have you ever heard of octane in gasoline? Octane.
I don't know. Sure. Not an expert on getting gas.
Octane is C8H18. So what would the simplest ratio be?
C4H9.
C4H9. So again, it's times 2. So what we're saying is that the molecular formula is always some whole number multiple of the empirical formula. What does that mean then about the weight of the molar mass of this compared to the molar mass of that? It's going to be twice, this one's going to be twice as big, this one's going to be 6 times as big, right? So the molecular formula is not the simplest ratio, which means it can be reduced, but it's always going to be a multiple of the empirical formula. Okay? Are you catching what I'm trying to get across here? So, there are three easy steps to determine the empirical formula. The law of definite composition says that no matter how much of a substance you have, it's got the same composition by weight. Water is always H2O. It's always going to be 2 grams of hydrogen to 16 grams of oxygen. It's always going to be the same percent. Doesn't matter whether you have a cup of water, a gallon of water, an ocean of water. It's always H2O. So, step 1, we're going to change, well, we're going to assume 100 grams of the substance and change percent to grams. So, if I know that water is 89.8%, whatever we calculated it to be yesterday, oxygen, it was 11.2% hydrogen, okay? That means that 11.2% of any amount of water is always going to be hydrogen. So I could assume 5 grams, I could assume 6.379 grams, I can assume any amount of grams, and it's always going to be 11.2% hydrogen. Let's make the math easy. If I assume 100 grams, what's 11.2% of 100? 11.2. So if we just assume 100 grams, that means I can just say, okay, well, that's how many grams I have. So in a nutshell, it's simplified, you're just going to change percent to grams. Then, we're going to go through, since the formula, this doesn't say 2 grams and 2 grams, that's 2 moles and 2 moles. So we got to change grams to moles. And what do we do? What do we use? What's the conversion factor?
6.02.
No, that would be moles to individual atoms. Okay, what do we call the conversion factor between grams and moles?
Is that the Avogadro?
No, that would be moles to atoms. What substance? What term do we have that has grams and moles in it? Grams per mole, which we call the molar mass, right? The molar mass. That's what we use. The atomic mass of the elements, or for the molecule, the molar mass, using the atomic mass of each element. Okay? Now that's going to give you a mole ratio, but it's not going to be a whole number ratio. The law of definite composition also says that the elements are going to combine in a small whole number ratio. We don't have parts of atoms in a molecule. We either have 2, we have 3, we have 4, but we don't have 2.3. Okay? So we have to have a whole number. So if we're doing this right, this mole ratio should be a whole number ratio, but to get the whole number, you're going to divide each mole value by the smallest mole value to get a small whole number ratio. Which That equals your empirical formula. I have just one that has it. You might actually like to use a book. I'm just looking for a good problem. There we go. Okay, so we have all this written down, right? So if you want to look in the textbook, and there's textbooks, there's a whole bunch there, not that one. Where are the rest of, there's one right behind here. I see 4 there, there's 4 there.
Did you say not this one?
No, that's the AP book. Your book is that one.
I know. Anybody else need this one?
That's an AP.
Yeah, you don't
Anybody
know,
else?
Ella, pass the AP stuff.
Okay, so I am on page 248. Page 248. So if we look at number 36 right here, determine the empirical formula of a compound that's given this percent composition. So we want to go through and we want to do the 3 steps that we just did. Okay? So I'm going to do it on this side. Okay, you have the 3 steps written right in front of you. I have them written on my brain. So step 1, so this is number 36. Step 1 is to do what?
Change the percent, or like change the percent.
Percent to grams. We're just going to assume 100 grams. So I can really just say I have 63.50 grams of silver. I have 8.25 grams of, what is that, nitrogen, and 28.25 grams of oxygen. Okay, that was a very challenging step 1. Okay? Step 2, convert to moles. How do we convert grams to moles? Okay, so what number do I look up for silver if it's number 47 on the periodic table?
It's like 107.9.
107.9 probably works good for me. So that's 107.9 grams per 1 mole. Where does grams need to go?
On the bottom.
On the bottom. This is on the top, so we're going to say 1 mole, 107.9 grams. Okay, somebody do that out for me.
Uh, 0.5885.
585 moles of silver. Okay, so we're going to do the same thing here, except instead of using 107, we're going to use for nitrogen 14.01, right? Okay, so somebody give me a number there. What are we going to do for oxygen? 16, right? It's 15.9994. We'll round that to 16. So does everybody understand where these numbers are coming from?
No.
periodic table, do you have it? Your
Well, I know where they're coming. Okay, you multiplied?
No, it's because it's on the bottom, oops.
Oh, okay, I didn't know you were multiplying, that's where I got.
Well, I'm multiplying, but it's on the bottom, so it's gonna actually be dividing. It's on top, you multiply, it's on the bottom, you divide. So it's 63.5 divided by 107, 8.25 divided by 14. So what's the second one equal?
0.5889.
Ooh, look at there. Almost the exact same number. And the last one? Anyone, the last one.
1.766.
Moles of oxygen. Okay, so now I have a mole ratio. That's step 2. I have a mole ratio, but it's not a small whole number ratio. But if this truly is the percentage of a compound, these should be in a small whole number ratio. So in order to find out what that whole number ratio is, how many times greater is each one, we're going to divide by the smallest one. This is my smallest mole value. So I'm going to divide by 0.5885. 0.5885. 0.5885. Now, obviously, what's this going to equal? 1. This is going to equal 1. This is going to equal 1. Now, it's not exactly 1, but it's pretty darn close. Okay? But what's the 1.766 divided by 0.5885 equal? I would say 3.
Yeah, it's like 3.000.
Yeah, so again, as long as you're within like 0.05 of a whole number, you can just round it to that whole number. So 2.95 is going to be 3, 3.05 is going to be 3, anywhere in that range. We get much farther away from that, we're going to have to do another step. But in this case, it's going to be 3. So my empirical formula is going to be Ag1N1O3. And then we can flash back to the previous chapter and say, okay, so what's the name of that compound? There you go, whoever just said that, silver nitrate. Do I need a Roman numeral with silver?
No.
No, it only has one oxidation state. Element number 47. Okay? Again, the only way you know is you look. Okay? So, 3 easy steps. Change percent to grams. Use the atomic mass, get moles. Once you have the moles, divide by the smallest one to get a whole number ratio. And that's your empirical formula. So let's see if you can do 37 just right there in your nose right below it.
Carbon, do you want us to do 12.01 or 12.011?
Either one, but I generally 4 is going to be no 12.01. And you're never going to go wrong using more. It's just you don't have to. I used to only use 3, but then over the years I've migrated to 4. On these particular problems, the more accurate you are, the more sig figs you use, the better the results come out. see everybody working, that means everybody kind of has an idea what to do. Just follow the yellow brick road, follow the 3 steps, you get there every time. Okay, do we all have an answer? So what's my first step here? What do I do? Take it to grams. 1 mole. Clay, what did you use?
12.01.
12.01 grams. When you divide that out, what do we get?
4.339.
4.339. Okay, same thing here, 1 mole. Now I always say 4, but with hydrogen I tend to use 1.01 versus 1.007, or actually be 1.008. But if you use 1.008, that's fine. If you use 1.0079, that's fine. I'm going to use 1.01. What does that give me? 12.9 what? 11 moles hydrogen. And then the same thing on the oxygen. 1 mole over 16 grams. Say that again.
2.172.
Okay, so now I have a mole ratio, but I need a small whole number ratio. So I divide by the smallest one, which is going to be this one. Okay, there's no need to really write this one out if you know that this is the smallest one, because we know that this is going to equal 1. 2.172, 2.172. I can tell already mathematically that's going to be a 2. Okay, 17 times 2 is 34. This is 34, so I'm going to just write it 2. So what does this one come out to? Write it 6.
Well, 5.99.
5.9 again. That's close enough for government work right there, as far as, you know, close enough to 6. So my empirical formula, as I'm going to write it above it just so everybody can see it, is going to be C2H6O. Right? That's probably ethanol. Okay, ethyl alcohol, but it could be many other things based upon how they combine. All right, so we good there? All right. Here's one that's not in the book. You're given 40.27% potassium. You're given 26.78% chromium, and you're given 32.96% oxygen. Okay? Now, we changed that to grams. I'm just going to assume it's grams. We're just going to do our same thing. 1 mole over 39.10 grams. 1 mole over 52.00 grams. And 1 mole over 16.00 grams. Somebody give me some numbers for these. Okay? We're doing the exact same thing. We're just taking, we're assuming we're changing this to grams, 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 and no need to rewrite it all out.
1.03.
1.03 moles of potassium, 515 moles of chromium, 2.06 moles of oxygen. So now we divide by the smallest one. Obviously, this one is going to be 1. It's going to equal 2. Oh shoot, I didn't do the right one. And this is going to be 4. That's not the one I want. I did the wrong compound. Okay? Alright, so that's the so K2 CrO4, which would be called potassium chromate. Okay? Well, it didn't hurt us to do one extra. Now I gotta do quick math. Uh, 16 times 7. 16 times 7 is 42, 112. Okay, so we're going to have 26.58. Let me start over here. 26.58% potassium. We're going to have 35.35% chromium. And we're going to have 38.07% oxygen. Okay, now everything looks very similar to the one we just did. Change again, we're going to change this to grams. Now, I don't ever, when I'm reading a problem, I don't ever just put percent down. I automatically just change it to grams. Times 1 mole, 39.10 grams. Same thing. 1 mole, 52.00 grams. 1 mole, 16.00 grams. This is the one I meant to do last time. So what do we get for the first one?
0.67, 9, it's just 6.80.
0.80. Okay, and that's going to be moles of potassium. Okay, so the next one?
Wait, Keith, why is it 9? Or why is it 8?
Because it's 6.79, but it just rounds up to 6.80.
Wouldn't it be 680 then, if you're rounding that way?
Depends on what place you're on now.
0.66.
Oh wait, no. Yeah, you're
Is that right?
The next one's 0.68.
Oh, this is 0.680?
It's like
Well, 'cause it's like-
it's 0.6799.
Yeah,
It's
Okay.
0.679.
0.680.
Wait,
So what did this one come out to?
that one is 0.67979.
Okay, 979. So if we want to just keep 4 sig figs, it'd be 0.6798. And then this one, it was still going to be just 0, 0, isn't it? Okay, but there's still, you can kind of see that those are pretty much going to be the same. And then the last one,
2.38.
one more digit,
8.
2.388.
Oh.
Did it come out exactly 2.38?
2.379.
Thank you.
We gotta spit out, no, it's not.
Okay, 4 sig figs. Everything's 4 sig figs. All right, so now we divide by the smallest one, which is going to be the 0.6798. So I know that's 1, that's 1. Divide this one by 0.6798. That's a horrible 0.6798. What does that come out to?
3.5.
3.5, right? Now, what did it come out to exactly?
3.4995.
Okay, 3.4999, so that's 3.5. Now, that is too far away from a whole number, just around to say it's a 3 or a 4. Okay? When it doesn't come out exact on the first one, it'll come out with 0.5 is what common fraction? A half. Okay? It's either going to come out to 0.5, it might come out to 3.33, which would be a third. It might come out to 3.32, 3.34, but we're still going to say that that's the third. Whatever the denominator is, we're going to multiply because we need to get to a whole number. So multiply this one by 2 to get to 7. But to keep the same ratio, we have to multiply this one by 2, and we have to multiply this one by 2. So we're going to get our empirical formula to be K2 CR2 07.
So if you were to get exactly 0.25, would you do it with 4?
Yes. Whatever the denominator is in the common fraction, when you change the decimal to a common fraction, whatever that decimal, whatever the denominator is, that's what you multiply by. So if it's 0.25, 2.25, you multiply by 4. If it's 2.33, you multiply by 3. If it's 2.5, you multiply by 2. 2.66, 2.67, multiply by 3. 2.75, you multiply by 4. Okay? So you just find that common fraction. Almost always it's a 0.5 or a 0.33. But we have to be within, the rule is within 0.05. That's my rule for when you can round to the nearest whole number. So 3.05, you can say 3. 2.95, you can say 3. 2.75, you cannot say 3. That you would have to multiply by 4 to get to the nearest whole number. Okay? Now, notice this happens when there's no 1. There's not a 1 thing in the empirical formula. It's a 2 to 2 to 7 ratio, not a 2 to 1 to 7, or there's no element that's just 1. That's when you're going to have to do this. That's very rare. It doesn't happen very often, except like on the test. All right, let's just be honest. Okay. So we're calculating the empirical formula. The only wrinkle is when you divide by the smallest, it doesn't come out exactly even. It'll be some common fraction, multiply by the denominator of that common fraction to get the whole number ratio.
So if it's above 5, then you can just round up, like to the next whole number anyway?
Well, no, if it's 0.05. Okay, so if it's 2.5, if it's 2.66, that's going to be 2/3, you're going to have to still multiply by 3. It's not until you get to 2.95 that you can round up. Okay? But again, it almost always turns out to be a 2.5 or a 2.33 or some number of 0.33, some number of 0.5. All right. Now, that's calculating the empirical formula. That's for ionic compounds, but covalent compounds use the molecular formula. Now, we already said that the molecular formula is always just some multiple of the empirical formula. So to go from the empirical formula to the molecular formula, we just have 3 more easy steps. So, to determine the molecular formula from the empirical formula. Empirical. Now, because it could, most of the time it's a continuation problem, I'm going to start with step 4. Okay, it's gonna be 3 more steps, but rather than saying 1, 2, 3 on this one, we're just gonna go forward. It's a continuation of this process. So step 4, determine, you just calculated the empirical formula. Determine the mass of the empirical formula. That's adding up all the atomic weights, the molar mass. And I'm going to refer to that as the empirical formula mass, EFM. So I don't feel like writing that out every time. Okay? So we just calculate the mass of the empirical formula, but because we know that the molecular formula is always some whole number multiple of the empirical formula. Therefore, the molecular weight is a whole number multiple of the empirical formula weight. So we calculate that, then we go divide, and here's the key word, the given molecular mass by the EFM to get a small whole number. Okay? So then you multiply the empirical formula by the small whole number to get the molecular formula.
So how do you write fast?
Because I know what I'm saying. So you guys have to copy it and just whatever. I already know what I need to write. 3 more easy steps. Okay? And then that's everything that we're going to be quizzed on. I'm letting the last of y'all finish copying. I need to pull the screen down, but that's going to cover it up. Everybody have it? Going once, going twice. I'm just going to pull the screen down. I'm not going to erase it. Now, let's look at number 38. What is the molecular formula of the molecule that has an empirical formula of CH2O and a molar mass, the molecular mass of 120? So, we already know the empirical formula, so we don't have to do steps 1, 2, and 3. So, I have step 4. I have to determine the mass of the empirical formula. What's the empirical formula? CH2O. That's the empirical formula. Okay? So I'm going to find the empirical formula mass, which is going to be 12.01 plus 2 times 1.01 plus 16.00 is equal to 30.03. Okay, this is my EFM. That's my empirical formula mass. Okay, it's just calculating molar mass. We already know how to do that. We've done that many times already this year, all through the first semester. So now, step 5, the given molecular mass is 120. You always divide this, the bigger by the smaller. 120.12 divided by 30.03. You can see that that's 4, right? So what's my molecular formula? C4 H8O4. Three more easy steps.
So basically it's unsimplified.
That's exactly right. We just have to know given the empirical formula mass dividing into the molecular mass tells us how many times we're going to multiply by. How much bigger the molecular formula is from the empirical formula. It's always a whole number. It never comes out to 3.5, 4.2, always a whole number. Okay? So, 39, now notice 39, a compound with a formula mass of 42.08, okay, that's my given molecular mass right there, is found, and remember U, what does that U stand for? What's the other unit that, you know, we do grams per mole, but what do we measure the actual mass of an individual atom? An AMU, right? Atomic mass unit, and so they just used U instead of AMU. All right, so I have the percent now. So what do I have to do?
Do everything. So like from the empirical.
You got to go through steps 1 through 6 on this one. Find the empirical formula. Then then do these 3 steps to find the molecular formula. So why don't we end the day, you guys doing that one?
Speed run it.
And then tomorrow we will go over this one, and we're just going to practice. I'm going to give you just a worksheet, and we're just going to practice some. And then you're going to have a quiz on Monday. Okay? Projects are due tomorrow. No homework other than that for tonight. Hopefully most of y'all are well on your way to getting that project done.
Do we have to present those?
No.
Okay.
I can do like during class or what?
Just, no, during class. You got to bring them in.
Get started there.
We got